Hello everyone, I am Surendra, Master Teacher of Mathematics in Vedantu. I have brought a series for ISI and CMI preparation. In fact, these sessions are very useful for JEE Advanced also. As continuation of my previous session in which I discussed a solution of 2019 UGA of ISI, today I will be discussing UGB. UGA was having 30 single correct questions, whereas UGB is having 8 subjective questions. Difficulty level of UGA is easy to moderate, you can say, but here in UGB you will be finding questions to be little difficult on as compared to UGA. So this is first question. Let us see what this is. Prove that the positive integer n that cannot be written as sum of r consecutive positive integers with r greater than 1 are of the form n is equal to 2 power l for some l greater than or equal to 0. Now to prove that, I will be proving two things. First is that suppose I am having r consecutive integers. Let us say my first integer is a, my second integer is a plus 1, and so on. And then we are getting a plus r minus 1, that is the last rth integer. So by using sum of n terms of AP, it will be r by 2 because total number of terms are r into first term plus last term. So it will be 2a plus r minus 1. So first I will prove that it cannot be equal to 2 power l for any integer l or for any positive integer l. In fact, in this question, they should have given L to be positive integer, then it would make better sense. Okay, so suppose, and to prove this, that it cannot be equal to 2 power L, I will take this to be equal to 2 power L. And by contradiction, I will be saying it is not possible. Dear all, please see, if this is 2 power L, then R cannot be odd integer. Because if odd, then 2 power L doesn't have any factor that can be odd. So this R has to be even. And if r is even, then 2a plus r minus 1 will be odd because 2a is odd, a is integer, r is even, so 2a plus r is even, minus 1 will be odd. Okay, and if that is so, then this product will have some odd factor into it. So this cannot be equal to 2 power L. I hope you are getting it. So we have got a contradiction. So this sum of any r consecutive integers cannot be equal to 2 power L. Now dear all, please listen carefully. This much should not be sufficient to conclude this question. Why I am saying so? Now what we have proved, that any number that can be written as sum of r consecutive integers cannot be 2 power L. Now what if there is an integer that cannot be written as sum of r positive integers? Can it be 2 power L, or can it also be in some case not equal to 2 power L? Okay, because here we have only proved that sum of r consecutive integers cannot be 2 power L, but the other case of this, how we can say that it will be 2 power L only? To say that, what we should do, we should prove the converse also. Like if I take some number n to be 2 power L, or rather not 2 power L, and then I will prove that n can be written as sum of r integers, r consecutive positive integers, r consecutive positive integer. Let us see how that we can do. Let me do it on the next slide. So suppose my n is not equal to 2 power L. So one of the case could be that my n is some odd number. Okay, case 1, that n could be odd number, and I think odd number we can take as 2m plus 1, and we know 2m plus 1 means we can write this as m plus 1. So this is sum of two consecutive integers are greater than 1. So this is true that if n is not 2 power L, and for this case is that n is odd, then I think we are done, that it can be written as sum of two consecutive integers. Now suppose this n is not odd, but n is some 2 power, let us say p, into some odd integer. Okay, I think this will cover all the even integers except those which are of the form 2 power L. Okay, and when I'm saying odd, it should be greater than 1. So this will be 2 power p into 2q plus 1. I am taking this. Okay, now this number, to show you that how this can be sum of r consecutive integers, please see what I'm going to do. I will write an AP whose middle term is 2 power p. Okay, and then I will add a term which is one more than this 2 power p, and then I will add one term that is one lesser than 2 power p. And similarly, I will add here 2 power p plus 2, one more I have added here, and here I will be subtracting, and it will become 2 power p minus 2. And this way, if I keep on doing, you can see, okay, I have added q terms here, and I have added q terms here. And by use of sum of 2q plus 1 terms of AP, or property that sum of first term plus last term is equal to second plus second last term, and so on, I think you can check this sum will be equal to this thing. Okay, now to give you one example, let us take 14. Let us take 14. 14 is 2 power 1 into 7. 7 is odd number. If I do the same thing to this, what you can see, I can write 2 here, 3 here, 4 here, 5 here. So 3 numbers I have written here, and I am writing 1, 0 and minus 1 here. Now, there is one very interesting thing here, why I have taken this example, that if you take this thing, you can see it is definitely sum is equal to 14, but it is not consecutive positive integer. You can check this minus 1 plus 1, 0, 2 plus 3, 5 plus 5, 10 plus 4, 14. So in this case, what we can do, we can ignore these 3 terms in the beginning, and we can say 14 is the sum of these 4 consecutive positive integers. And this kind of situation, whenever it will come, okay, we can ignore that many of terms, so that negative terms are, negative terms are ignored. For example, here, suppose I was taking 2 power p minus q. My this term would have been, I think, 2 power p minus 2. Yeah, that's correct. And the next term would have been 2 power p minus q plus 1. Okay, now suppose this is negative. Okay, then this will be 1 more than this. Then similarly, 2 power p minus q plus 2, that will be 1 more than this, and so on. Okay, so at some point of time you will get 0 also. Then you will be having terms which will be 1 more than this 0, and then next term, then next term, and definitely 2 power p is positive. So ultimately, after some time, these terms will be only positive. But you can definitely count these number of terms in which sum will be 0, and you can say that this number 2 power p into odd can be written as sum of r consecutive positive integers, where my first integer starts after this term. After this term means the sum where it was 0. So we can start from here. So this is how we can say that any number that is not of the form 2 power l can be written as sum of r positive integers. A number that is of the form that can be written as sum of r consecutive positive integer, that cannot be 2 power l. So I think we have proved any number that is not 2 power l if and only if it can be written as sum of r consecutive positive integers. So I think we can say that very safely that n, if not sum of r consecutive integers, has to be 2 raised to the power l. So this completes the solution of this question. Okay, chaliye, let us move to the next question, that is question number 2. Here we are given that f0 comma infinity to r is defined by fx is equal to limit n approaches to infinity cos raised to the power n of 1 upon n power x. We have to prove that f has exactly 1 point of discontinuity, and we have to evaluate this f at this point of discontinuity. Let us see how we will do this question. First of all, please understand, because my x belongs to 0 to infinity, that means x is greater than 0. So we can say that n power x, where n is approaching to infinity, will be definitely approaching to infinity, isn't it? Because if x is positive, and if we are raising it to some number that is tending to infinity, this value will be approaching towards infinity. Okay, dear all, let me tell you, whenever we have to think about this, we should think this way, that it is limit n approaches to infinity and n power x. Now whatever x you choose, by making n arbitrarily long or large, actually, I think this will always be approaching towards infinity. Some people may think that x, when it is very small, shouldn't it becomes approaching to 1? So dear all, let me tell you, whatever x, however small x you take, by varying n towards arbitrarily large, this n power x can become infinite. So this, for x approaching to x greater than 0, this limit n approaches to infinity, I can say n power x will be infinite. And 1 upon, again let me write this way, n approaches to infinity, 1 upon n power x will become 0. And if it is 0, I think this cos of 1 upon n power x will be becoming towards 1. Okay, and this 1 is raised to this, raised by n, which is approaching towards infinity. That means here we should be, we are having a form of 1 power infinity. So this cos of 1 upon n power x whole raised to the power n is actually 1 power infinity form. Now to solve this 1 power infinity form, what we can do, we can write this fx to be equal to one very standard case. If you remember, let me remind you that 1 plus fx into raised to the power gx for some x approaches to a, and this for x approaches to a, fx approaches to 0, and limit x approaches to a, gx approaches to infinity. So you can see it is actually 1 power infinity, and in this case there is a standard method. We write this to be equal to e raised to the power limit x approaches to a into fx into gx. I think that is something very standard, we can use directly. There is no need to prove it. Now using this thing, I think this fx can be written as e raised to the power limit n approaches to infinity. Now dear all, this cos 1 upon n power x itself is 1. So to write this in the form 1 plus fx, where fx approaches to 0, I need to write this as cos of 1 upon n power x minus 1 into n. This power will be multiplied here. Okay, now to find this limit, what I will be doing, I will write this as e raised to the power limit, let me just remove this, e raised to the power limit n approaches to infinity. What we can do, we can rationalize it. Rationalize means I can multiply by cos of 1 upon n power x plus 1, and in the numerator, if I do the same thing, it will become minus sine square 1 upon n power x into n. Okay, now if n approaches to infinity for all x, as I have shown you, 1 upon nx approaches to 0. So what I can do here, I'll write this as limit n approaches to infinity, and this cos 1, the cos 0 will be 1, this will be 1, so we can write this as n by 2 into minus sine square 1 upon n power x, and to make it a standard limit, I think I'll be multiplying and dividing by 1 upon nx square, and I'll be multiplying here 1 upon n power x square, and this way this thing will become equal to 0, because it is sine x upon x form where x is approaching to 0. So here what we are getting, it will be e power limit n approaches to infinity. This is 1, so I can write this as minus 1 by 2, and the power of n would be 1 minus 2x. You can check 1 minus 2x. Now here the limit will depend upon the value of x. Suppose my x is equal to 1 by 2. If it is exactly equal to 1 by 2, I think this power will become 0, and here it will be 1. because this n power perfect 0 will be 1, so it will be actually e power 1, not 1, it will be e power 1. If I take x greater than 1 by 2, if x is greater than 1 by 2, this power will be negative. 1 minus 2x will be negative, and if it is negative, so infinity power negative, let me tell you, if n is approaching to infinity and there is a power negative, that means 1 upon n power positive, where n is infinity, it has to be 0. So if it is 0, then I think for x greater than half, this will become 0, and e power 0, that means I will be having 1 here. Now similar to this, if x is less than 1 by 2, then this power will be positive, n power positive will be infinite, and e power minus infinity means it will be 0. E power minus infinity, again I am repeating, as x is less than half, this 1 minus 2x will be positive, n power positive will be infinite, minus half multiplied, so it will be minus infinite, e power minus infinite is 0. So this is how we can see that x is equal to 1 by 2 only. This function is discontinuous. That's the point of discontinuity, and the value of function at this point is e. So if I have to write the answer, let me write it here. For a part, show that this has exactly 1 point of discontinuity. So that point is x is equal to half, and in the b part, the value of function at that point, as you can see, we have calculated, it is coming out to be e. So this completes the solution of this question. Easy question, but little tricky question. It could have been confusing in the exam because this 1 upon nx could have been little confusing. Now coming to the next question, that is question number 3. This says omega is equal to z equal to x plus iota y belongs to complex number c, and mod y is less than or equal to 1, and fz is equal to z square plus 2. Then draw the sketch of f omega equal to fz such that z belongs to omega. So first of all, to know what is my omega, please see, omega is just a region of Argand plane in which the imaginary part is between 1 and minus 1, because mod y is between 1 and minus 1. So this is how my omega region would be, where this is y is equal to 1 and here this is y is equal to minus 1. So between these two lines, our region is actually omega. Now if I choose my z from omega, then where this fz will be mapped to, that is our question. So here please see, I can write this fz is equal to x plus iota y whole square plus 2, and this will give you x square plus 2 minus y square plus iota into 2xy. Simple formula, nothing else. So fz will be this thing. Now we have to see that corresponding to some x comma y of this omega, how this real part would be, how this imaginary part would be, and how this fz will be shown on the Argand plane. Now to do this, let me take this real part as capital X and this 2xy as capital Y, the imaginary part, capital X, capital Y. And now I will draw the graph of this f omega that we are saying, because f omega is the set of all such fz where z belongs to omega. So this will be my capital X and that will be my capital Y. Now to do this, what I will do, because dear all, please see here, small x belongs to all real number because there is no restriction on x, but my y is between 1 and minus 1. Okay, so what I will do, I will try to make a relation between x and y for some taken y. Or let me do one thing, for let us say y is equal to beta. Okay, and beta can be anything from minus 1 to 1. So for y is equal to beta, I think we can say this capital X would be x square plus 2 minus beta square, and this capital Y would be 2 into x into beta. Now I will eliminate capital X, small x, which is from minus infinity to plus infinity, to get a relation directly between x and y, and from that we will be able to observe that which kind of curve it could be. Okay, now this will be, I can write this capital X now as capital Y upon 2 beta whole square plus 2 minus beta square. Let me take this to the next slide. What I got x is equal to capital Y square upon 4 beta square plus 2 minus beta square. I think that is what we have got. Now if I write this as a relation in capital X capital Y in a standard form of some standard curve, you can say this y square would be equal to 4 beta square into capital X minus 2 minus beta square. Now you can recognize this curve easily. This is actually y square is equal to 4ax form, 4ax minus h form. So that's a standard parabola, or you can say right opening parabola. Right opening parabola, in which you can see the length of latest rectum is 4 beta square, and the vertex here is 2 minus beta square comma 0. Okay, now please see this beta is actually ranging from -1 to 1. So if I try to draw a diagram for this curve, what we can see, this vertex will be lying between 2 to 1, because beta square will be from 0 to 1. Beta square will be from 0 to 1. So here this 2 minus beta square will be from 1 to 2. So my vertex will be from 1 to 2. And latest rectum will be 4 beta square. For example, if I take beta is equal to 1 or minus 1, if I take beta is equal to 1 or minus 1, in both case my vertex will be 1 and my latest rectum will be 4. So this kind of parabola would be the answer. If I take other extreme, in which beta square is 1, my vertex will be at 2, my beta square is at 0, beta square is at 0, then vertex will be at 2, but latest rectum will become 0. That means this will be nothing but a line aligned towards x-axis like this. Now if I take any number in between, I think if I take beta square is equal to half or something like that, this vertex will be here, 1.5 you can say, and my latest rectum will be, in this case, I think 2. Yeah, 2. So you can see this will be a smaller parabola, smaller in the sense of latest rectum, and this will be going with this, will be going like this. Now if I try to plot all the betas from -1 to 1, beta square will be from 0 to 1. You can see the vertices will be lying here to here, and parabolas will be lying like this. So all the region lying inside this parabola, inside means where focus of a parabola lies. So this is where my region will be for this f omega. F omega would be this inside the parabola of this thing. In fact, we can give the equation of this boundary parabola, that will be y square is equal to 4 into x minus 1, I think. Yeah, x minus 1. So that is the answer for this question. Interesting question. Okay, now coming to question number 4. It says f r2r be a twice differentiable function such that 1 by 2y integration x minus y to x plus y ft dt is equal to fx for all x belongs to r, y greater than 0. Show that there exists a comma b belongs to R such that fx is equal to ax plus b for all x belongs to R. That means we have to prove that fx would be a linear function. Now they have given f to be twice differentiable function, so we are very much free to differentiate it using Newton-Leibniz formula. So if I differentiate both sides with respect to x, differentiation with respect to x, so y will be considered as a constant. Here you can see x belongs to R and y is some positive integer which is independent of x, because we are not given any relation of x with y, so we can assume that it is independent from x. So if I do the differentiation with respect to x, we will be getting 1 upon 2y, then differentiation of upper limit, that is 1, and this upper limit will be going in place of t, so this will be x plus y here, minus differentiation of lower limit, that is also 1, and then in place of t I will be putting x minus y here, and that is equal to f dash x. Okay, now we can do it by graph also, but I think the better approach I'm thinking of doing this question is that I can write this as f of x plus y minus f of x minus y is equal to 2y into f dash x. Now, as y can also be considered to be a variable, keeping x fixed at some number and varying y, I think I can do the differentiation with respect to y also. Differentiating with respect to y, now what we will be getting, f dash x plus y, and now it will be plus f dash x minus y, and on the right hand side it will be 2 f dash x. Okay, so one interesting thing what we are getting here is that this f dash x, that is derivative at any x, is always the mean of derivative of the function at x plus y or x minus y. The same thing could have been seen from this relation also. Here what you could have said that f dash x is actually equal to the slope of the chord joining x minus y to x plus y. You can see, you can define like this, that my x coordinate is x minus y coordinate is, let us say, f of x minus y. That is one point. And another point you can take as x plus y, comma, f of x plus y. So if you join these 2 points and take their slope, I think this left hand side will be the slope. So this chord joining these kind of 2 points having slope same as f dash x. So whatever y you choose, that means x is so located that if you take differentiation, it will be equal to the slope of a chord joining 2 points, and these 2 points are such that they are equally spaced about x. One at x minus y, one at x plus y. And I think such is a property of parabola also. If you differentiate and if you take if you have done the question of Rolle's theorem, or I think Lagrange's mean value theorem, you will find that for any 2 point on the parabola, the C of that Lagrange's mean value theorem comes exactly at the midpoint. So this gives you the feel of that it could be a parabola, but I think that I'll get in another way also. Please see how, if I differentiate this once again with respect to y, it will become f double dash x plus y minus f double dash x minus y is equal to 0. What exactly this says, because x I can choose anything. Okay, then x plus y and x minus y are kind of, 2 arbitrary numbers. You can take x plus y as t. Okay, then this f double dash t here will become equal to f double dash, I can write y as t minus x, and y as t minus x means it will be 2x minus t. So I am free to choose any value of x. That means my second derivative has to be constant, because it has to be true for all t and all x. Okay, so what we have concluded so far, that its second derivative will be constant. And in fact, the same thing I was saying from this thing also, that it would be a parabola, and you know that in parabola second derivative is a constant value. Okay, let me take another slide. So to do the further part of this question, let us take this new slide, and here, because we have proved that f double dash x is a constant, and you know that f double dash x constant means it has to be second degree polynomial. So fx can be taken as px square plus qx plus r. So only thing we need to prove here is that p will become 0. Now to do this thing, we will use this relation once again. How? Please see, 1 upon 2y into, I think integration of this thing can be written directly. I just need to change this x by t first, and then doing the differentiation, it will become p t cube by 3, then q t square by 2 plus rt, and this limit is x minus y to x plus y, and this has to be equal to fx. That means it will be px square plus qx plus r. Now let us put the limits. So this will be 2y here, p by 3 into this t cube. I will be first putting x plus y whole cube, then I will be putting x minus y whole cube and taking the difference of these two. And similarly q by 2 t square, it will be x plus y whole square first minus x minus y whole square then, and then r into x plus y minus x minus y, and this has to be equal to px square plus qx plus r. Now please see how much, what will be the things we will be getting after simplification. 1 upon 2y here, and p by 3 into x cube will get cancelled. Okay, I think the another term will be 3x square y, and here it will be getting added because there will be 2 minus minus, so plus. So here we will get 6x square y, and I think then 2y cube also. Okay, then for this q by 2 into this thing, x square plus y square term will get cancelled. This will be 4xy, so I can write this as 2q into xy, and here I think it is just 2ry, and this we need to be equal to px square plus qx plus r. Okay, if we divide by 2y inside it, what we will be getting, I think this will be 2y will be cancelling it like p by 3 into 3x square plus y square only, then plus 2q xy, I think this will remain only qx and here only r, and this should be equal to px square plus qx plus r. So you can see both sides to be exactly identical. Okay, I think qx rx we are already getting, but here to make it identically equal, I think we need to have p is equal to 0, because y is positive, you cannot have these things to be equal. Okay, so p, if it is 0, that means my fx is actually a qx plus r form, or you can say ax plus b form, that is linear. So I think this completes the solution of this question. Okay, now coming to question number 5, which says a subset S of the plane is called convex if given any 2 points x and y in S. The line segment joining x and y is contained in S. A quadrilateral is called convex if the region enclosed by the edges of the quadrilateral is a convex set. So what they are trying to say that if your quadrilateral or a convex set is such that you join any 2 points of it, an entire thing is lying inside the region, something like this. But if you draw a quadrilateral like this, in this case you can see if you join these 2 points, okay, then the portion of line joining these 2 points is lying outside the region. So this will be concave, and that will be convex. That will be convex. In fact, one more thing you can see that for any convex quadrilateral or polygon, this angle has to be less than 180. Every angle should be less than 180. But in case of concave, you may have 1 or 2 angles that are greater than 180 also. Okay, so this thing was only to explain you what is convex set. Now they are saying, show that given a convex quadrilateral Q of area 1, there is a rectangle R of area 2 such that Q can be drawn inside R. Now I will make 2-3 cases for this thing. First of all, we should understand for any quadrilateral, we have to have at least one of the angle that is greater than or equal to 90. So I'm making one quadrilateral, something like this, and you can see one of the angle is greater than 90. Maybe I can ignore that this is not greater than 90. You can think of that it's acute only. Actually, my purpose here is that I will be drawing a diagonal like this. Let me call this quadrilateral as ABCD. Okay, and then what I'm going to do, because these two angles are acute, okay, so I can draw a diagonal passing through A and C, and then I can draw two lines. So two lines, one passing through B parallel to AC, and one line parallel to D and parallel to AC, and then we can draw a rectangle like this. This rectangle is such that this line joining A is perpendicular to AC, and because these three lines are parallel, so here we will get a rectangle. These two sides are parallel and these are perpendicular to AC. Now what you can see, suppose I call this rectangle as PQRS. Okay, so it can be seen that area of this PQCA is 2 times the area of triangle ABC. It is direct conclusion from the fact that base are same, height is also same, but because one of them is rectangle, one is triangle, so that because of factor of half, this PQCA will be 2 times. Similarly, area of rectangle ACRS is 2 times area of the triangle ACD. Okay, now if I join both of them, I think we get, if we add both of them, we get area of PQRS, and that is equal to 2 times area of this quadrilateral ABCD. And this is 1, so this becomes equal to 2. So you can see that we can have a rectangle of area 2, so that this Q, that is quadrilateral Q, is drawn inside the R. So that is one of the case. Okay, now I'll tell you a few more cases, because here we assumed that these two angles are acute, or at least rectangles, the diagonal AC was such that the two sides passing through this vertex A and through C, they were making these angles, let us say alpha, beta, gamma, delta. They all were acute. Why I'm saying so? If alpha is not acute, alpha is obtuse, then the rectangle we would be making, that will be lying outside the quadrilateral. Let me show you the another diagram. You can see here I have taken this quadrilateral is ABCD. This is B here, quadrilateral is ABCD here. Now you can see this one is right angle, this is obtuse, and this one is also obtuse. Now if you join the diagonals, you may not be able to make rectangle the way we made in case number 1. Okay, in case 1, what was important? These angles AB, alpha, beta, gamma, delta, all were acute. Here you may not get, like if I join B with D, let me just try with this way. Okay, and because this angle, if it is obtuse, you can see my rectangle will be going like this, and in this case this quadrilateral will be going outside. So this case, I think that previous method will not work. Then how we can do it? Let us see. In this case, what I have done, ABCD is a quadrilateral, that given in the question, and I have drawn a rectangle whose base is AD. Okay, and from AD, actually both the angles are acute, alpha here, and maybe I can call this as gamma here. Okay, and then through C I have drawn a line parallel to AD, and then from A perpendicular to AD, and from D perpendicular to AD, lines are drawn so that PQDA is rectangle. Okay, I think simple observation may do this question for us. Please see, I have drawn perpendicular from C to AD. Similarly, I have drawn a perpendicular from B to CR. Okay, and similarly this is perpendicular to this. In fact, all these lines which we are seeing, they are perpendicular to the line of their intersection, at their point of intersection, you can say. Now here you can see this area, if it is A1, this also has to be A1, because CQDR is a rectangle. Similarly, this area, if it is A2, this will also be A2. Similarly, if this is A3, this is also A3. So now you can see my area of quadrilateral, that was 1. Okay, area of the quadrilateral is actually A1 plus A2 plus A3 plus A4, and this is equal to 1. Whereas area of rectangle in this case is actually 2 times A1 plus A2 plus A3 plus A4. Okay, but I think in this rectangle, uh, in this rectangle, A4 is only once, so I will be subtracting A4, and there is A5 outside that is also included, which was not there in the quadrilateral. So if I am able to prove that A4 is bigger than A5, I think we can say this area of rectangle will be lesser than 2. Okay, now do this thing. What I am going to do, I have drawn this angle as alpha and this angle as beta. Now you can see alpha has to be greater than beta. Why I am saying so? Because this line is parallel to this line. Even if this AB was extended like this angle would have been same as alpha. And because it's a convex quadrilateral, so this angle beta has to be lesser than alpha. I hope that is clear. Now please see. This A5 area, is actually, you can see, length from this place to this place. I can call this as AB into cos alpha. This one side, A5 is this equal to this, so AB cos alpha into the other side is BC sine beta. BC sine beta. Okay, and A4, if I do, A4 is this thing, it is actually opposite. You can see it will be AB sine alpha into, that will be BC cos beta. Okay, now you can see that A4 minus A5, if I do, that will be AB into BC common, AB, BC common, and what we are getting? We are getting, I think, A4, I have written this as first, so I think this comes out to be sine of alpha minus beta, if you can check. Okay, and because alpha is a bigger angle than beta and they both are acute, so this has to be positive. So that means A4 is bigger than A5, and hence this area of rectangle will be less than 2. So you can see in this case, we have drawn a rectangle whose area is even lesser than 2 and it is still able to contain this quadrilateral. So in this case, when two angles were obtuse, okay, we have done this way. In convex polygon, convex quadrilateral, actually, there is one more possibility that we may have three internal angles to be obtuse, 1, 2, and 3. Third has to be acute in that case. I think in this case it is much easier. You can see this ABCD is the polygon here, ABCD is the quadrilateral here, and let me call this as P, Q, R, and D. P, Q, R, and D as the rectangle. So you can see the area of quadrilateral, which is A1 plus A2, A1 plus A2 plus A3, and there is one more left out area, that is A4. So A4, that is equal to 1. Whereas area of rectangle, if we see, it will be 2 times A1, which covers this and this, plus 2 times A2, which covers this and this, plus 2 times A3, which covers this and this, but only A4. If I write A4 here, I have to subtract A4 here, so that will be lesser than 2. So once again, you can check in this case, this rectangle is covering this quadrilateral whose area is 1 and area of rectangle is lesser than 2. So rectangle of area 2 in all possible scenarios, you can see can contain the quadrilateral. So I think this is how it is done, hence proved, I can say. Now coming to question number 6, it says for all natural number n, let an is equal to root over 2 minus root over 2 plus root over 2 and so on, root to n many radical signs. And we have to prove that an is equal to 2 sine pi upon 2 raised to the power n plus 1. Now to do this question, let us understand, first of all, this root 2, I can take this as 2 cos pi by 4. Okay, this trick has been used in many standard problems, so you may get idea from this, or you may have started with n is equal to 2. You can prove this thing for n is equal to 2, then for n is equal to 3, and so on. But here I am telling you the direct method or general method for n. So root of 2 plus root 2 would be, please check, 2 plus 2 cos pi by 4. If I take 2 common and use formula of cos 2 theta, I think this will become 2 into 2 cos square pi by 8, which after removing this under root sign will become 2 cos pi by 8. Okay, so what you can see, I have removed 2 under root signs and I got 2 cos pi by 8. Similarly, if it is root 2 plus root 2 plus root 2, in which 3 under root sign will come, this will become 2 cos pi by 16, okay, and so on. So what they have given an here, I think I can remove these n minus 1 under root signs and I will be getting 2 minus 2 cos of pi by 4, and you can check when there was 1 under root sign was removed, nothing was divided. When 2 were removed, we divided by 2. When 3 under root sign was divided, then we divided this pi by 4 by, I think, 4 here. So I think when I am dividing, when I am removing n minus 1 under root signs, here we will be getting 2 power n minus 2 extra. Okay, so this will give you 2 minus 2 cos pi upon 2 power n. Now this time, once again, I can use cos 2 theta formula, but this time we will be getting sine of pi upon 2 power n plus 1, and here there will be square. So this gives us 2 sine pi upon 2 raised to the power n plus 1. So I think this is how this is done, and I think second part is much easier once you know this an, because limit n approaches to infinity, we are given an, that is 2 sine pi upon 2 power n plus 1, and I will write this 2 power n as 1 upon 2 power n like this, and then we can write this also as sine of pi upon 2 raised to the power n plus 1 pi upon 2 raised to the power n plus 1. Okay, this 2 will be coming here. Yeah, that's correct. And for that I have to multiply with pi, and this will become sine x upon x form, where x approaches to 0. So this answer will become equal to pi. So the answer for this question, B part, is pi. Okay. Now coming to question number 7, one tricky question. It says f be a polynomial with integer coefficients. Define a1 is equal to f naught, a2 is equal to f of a1 is equal to f of f naught, and an is equal to f of an minus 1 for n greater than or equal to 3. If there exists a natural number k greater than or equal to 3 such that ak is equal to 0, then prove that either a1 is equal to 0 or a2 is equal to 0. This question is from one of the prestigious exam we call as Putnam from its previous year. You can check the data is slightly changed, some variables are some changed, you can see what exactly difference is. But here what you can see, suppose I take a1 is equal to 0, although let me make it very much clear that we have to start with ak equal to 0, then we have to prove either a1 will be 0 or a2 will be 0. But just a scenario, if a1 is equal to 0, then you can check a2, which is f of a1, will be f of 0, and f of 0 is a1, but it is 0. So you can see all these a1, a2, this way if I do, all these numbers will be 0, so ak will also be 0. So there is a scenario that if a1 is 0, ak will be 0, or you can say that ak can be 0 in one of the scenario when a1 is 0. But let us now focus on whether ak is equal to 0 implies a2 equal to 0 or not. Okay, now to do this thing, what I am going to do here, that suppose we are given ak is equal to 0, then f of ak will be equal to ak plus 1 from this definition, and because ak is 0, so this f0 will be equal to AK plus 1, but F0 is A1, so this AK plus 1 becomes equal to A1. So that is one thing. Now similar to this, if I apply once again, f of AK plus 1 will be AK plus 2, okay, and because AK plus 1 is A1, so this f of A1 will be equal to AK plus 2, and f of A1 is A2, so we have proved from this thing that f of A of K plus 2 is equal to A of 2. So these two things we have proved. Tricky question, but let us do it step by step. My next step here would be, first I will prove that because this function f is with all integer coefficients, okay, so this a1 is just f0, that is the constant term, so it will be integer. Now a2, which is the value of this polynomial at a1, that is integer with integer coefficients, so this will also be integer. So this way I can say a3 is also integer, and so on. All these a1, a2 up to an, they all will be integer. Now what is the implication of this thing? If a1, a2, they all are integer, and I write an minus 1, okay, then this means it will be f of an minus 1 minus f of an minus 2, okay. Now if I take f function to be a polynomial of capital N degree, let me write this function also here. Fx is equal to b capital N into x power capital N plus bn minus 1 x power n minus 1, and so on and so on, plus b1 x plus b0. Okay, so here you can see this f of an minus 1 minus f of an minus 2, if I do, I can take b capital N common, and here an minus 1 power capital N minus an minus 2 power capital N. Similarly, next term would be b capital N, and here an minus 1 once again, but power will be capital N minus 1 minus an minus 2 here, capital N minus 2, and power will be capital N minus 1. Let me correct it. And so on and so on. The last one would be b1 into an minus 1 minus an minus 2. So what you can notice here, all these terms are such that you can take an minus 1. Let me write in the next step that what we can see, that this an minus 1 can be written as, in all these brackets I can take an minus 1 minus an minus 2 common, and whatever is remaining, you can see because they all are integers, I can write this as integer. Okay, so this concludes one very important thing here, that an minus 1 minus an minus 2 will be dividing an minus 1. Okay, one lesser subscript you can see will be dividing one upper subscript. So I can say this using same thing, that a1 minus 0 will also be dividing a2 minus a1. It can be proved similarly, or you can think of a1 was f0, and you can say a0 is 0. You can take that way also, and then you will be able to prove that a1 minus 0 divides a2 minus a1, and this will divide a3 minus a2, and so on. Okay, and we will be getting ak minus 1, and then we will be getting ak plus 1 minus ak, and so on. So you can see this a1, let me use this space here, a1 divides a2 minus a1, and so on. After skipping few terms, what you can see, this ak plus 1, as you can see, I proved it was a1, and ak we are given as 0, so this divides a1 here. This becomes a1, sorry, this becomes a1. So a1 divides a2 minus a1, and a2 divides this, and this divides next, and so on, and this term here is becoming only a1. So what you can say now that A1 divides A2 minus A1 and this divides A1, I think that is only possible if my A2 minus A1 is equal to either A1 or minus A1. Not only A2 minus A1, all these terms that are lying in between, they will also be like this. A3 minus A2, AK minus 1, they all will be either A1 or minus A1 and so on. I will write till AK minus 1. Now, if I add all these terms, A1 minus 0 plus A2 minus A1 and so on till AK minus 1, you can check it is becoming kind of VN method. So A1 will be cancelled, then A2 will be cancelled, only AK will remain, but that too is 0 because we are given in the question. So sum of all these terms are 0 and each term is either A1 or minus A1 as I claimed by this logic. Okay, so some of them will be plus A1, some of them will be minus A1. Okay, that means there will be some terms, you can say two consecutive terms, out of which one of them will be A1 and other will be minus A1. What I'm claiming that some of them will be A1, some of them will be minus A1. Okay, so there will be, if I call this as first term, I call this as second term, and I call this as kth term. So among these 1, 2, 3 up to kth term, there will be two consecutive terms. One of them would be A1 and one of them would be minus A1. So I can say that sum, let me call that as AM minus 1 and then AM minus 1 minus AM minus 2, or maybe I can use the next one. So I will be saying AM plus 1 here and AM here. So AM gets cancelled and we are getting AM plus 1 and this will be 0 because one of them is A1 and another of them is minus A1. So AM plus 1 is equal to AM minus 1. So this is what we have got here. Okay, let me use next slide. So we proved that AM plus 1 is equal to AM minus 1. Now, if I take the value of this polynomial over these numbers, so this will be like this. So here we will get AM plus 2 is equal to AM. Now, if I keep on doing this way, I think this AM was in between here. Okay, so we will be getting AK to be equal to AK minus 2 and then AK plus 1 to be equal to AK minus 1, and ultimately this is what we are looking for. AK plus 2 is equal to that will be equal to AK. And we proved in our this first slide that AK plus 2 is A2 and AK we started with 0. So you can see A2 is coming out to be 0 here. Okay, I think for A1 we may not be able to conclude whether it will be 0 or not, but yes, for A2 will definitely be 0, but yes, if A1 is 0 then also AK will be 0. So there will be mixed kind of scenario, you can say that A1 0 then also AK 0, and some cases when A2 is 0 then also AK will be 0. In fact, when A1 was 0, A2 was also 0. So we are actually getting that A2 will be 0 in all possible scenarios. So this completes the solution of this question. It was a tricky question. I hope you have understood it. Coming to this last question, that is question number 8. Consider the following subsets of the planes. Subset of the plane C1 is x comma y such that x greater than 0 and y is equal to 1 upon x. And C2 is x comma y, x less than 0 and y is equal to minus 1 plus 1 upon x. So you can see this is rectangular hyperbola, one of the branch. The first one C1, this will be like this. Okay, And in C2, this is another again rectangular hyperbola, but we have lowered the value by -1 or lowered the value by magnitude 1, and this is for x less than 0. So if I draw this line y is equal to -1, okay, so this is how my other C2 would be. This is C1, this is C2. Okay, now we are given 2 points P equal to x comma y, Q is equal to u comma v of the plane. Their distance is defined by under root of x minus u whole square plus y minus v whole square. That is just a normal definition, nothing special about it. Now we have to show that there exists a unique choice of P naught at C1 and Q naught at C2 such that distance of P naught with Q naught is less than or equal to distance of P with Q for all P belongs to C1 and Q belongs to C2. Now please listen carefully. Actually, we need to find a point P naught here and maybe Q naught here so that the distance between these 2 points is least possible among all possible pairs, one of the point lying on C1 and other point lying on C2. That is what we need to prove. I think we can use a simple concept that least distance lies along common normal. In fact, among common normal, we may get maximum distance also. In fact, these least or maximum distance which I am talking about, they are always local minimum or local maximum. So we have to verify also whether using this common normal thing we will be getting absolute least or not. To do that, let us do one thing. Let us take P naught as t comma 1 upon t and Q as s comma minus 1 plus 1 upon s. Okay, now because P naught Q naught will be along common normal, okay, so I will be writing the slope using 3 methods. Okay, so slope of normal at P naught, you can check, it will be just differentiate with respect to x, you will be getting minus 1 upon x square. And because slope of normal we are talking about, so minus 1 upon slope of tangent we will be getting this to be t square. Easy thing, it can be done directly. Similarly, slope of normal at Q naught, it will be, I think, s square. So we will be getting t square is equal to s square, and also this slope should be given by slope joining 2 points. So it will be 1 upon t minus 1 upon s plus 1 whole divided by t minus s. Okay, I can write the last term also as, I think, minus 1 upon t into s plus 1 upon t minus s. These two terms, if I take LCM, s minus t upon ts, t minus s will get cancelled, minus 1 upon ts plus 1 upon t minus s. And this is here t square is equal to s square also. So if I simplify it, or let me write it once again, t square is equal to s square is equal to minus 1 upon ts plus 1 upon t minus s. Okay, now this means t will be equal to minus s. Why I am saying so? T cannot be equal to s because t is positive and s is negative. So this t will be equal to minus s, and then if I combine these two things, so writing s is equal to minus t, I will be getting t square is equal to 1 upon t square plus 1 upon 2t. Okay, this gives us a biquadratic t power 4 minus 1 upon 2 into t minus 1 is equal to 0. Okay, so the root of this biquadratic will give me where common normals are possible. Okay, and then we will check whether these common normal will be giving least distance or not. Let us see. First of all, the root of this, if I check, this is a biquadratic, it will be having infinity values at both ends, minus infinity and plus infinity. The value at 0 is 1. If I call this as ft equal to t power 4 minus t by 2 plus minus 1, you can see f dash t comes out to be 4t cube minus 1 upon 2. Okay, and if calling this is equal to 0, I think will give us only one value, that is t is equal to I think 1 upon 2 only. T is equal to 1 upon 2. Yeah, that is correct. And if we check the sign of this f dash t at 1 upon 2, it will be positive here, it will be negative here. Okay, so for this ft, this point will be point of minima. In fact, we can draw the graph of ft. I'm not talking about these graphs C1, C2. I'm talking about the graph of ft. The value at 0 is 1, minus 1. At 1 by 2, it's minimum. So it will be going down till 1 by 2. And then it will be going up because this was the point of minima. And because this is the biquadratic, it has to move up. So there will be one point where it will become equal to 0. My t is positive because I have taken this t on C1. So I need not to make this part of the graph, and this point is not relevant to us. So we can see this ft will become 0. So ft is equal to 0 only at one point. Only at one point. You can call this as t is equal to, let us say, t naught. Okay, and this t equal to t naught will be the point where p naught, q naught will be having a common normal. Okay, and here you can see this common normal will either give us local minimum distance or local maximum distance. By a simple observation also, it can be said directly that if you go any further from this point to here or this point to here, distance is going to become more than what P naught Q naught will give us. In fact, there is a possibility that we may have points lying on C2 and C1 such that the distance is infinity also. So there is no question this becoming a point of local maximum. It has to be point of local minimum. So this T naught given by this Ft is equal to 0 will give us P naught, and then correspondingly we can find Q naught also. And we need not to find P naught, Q naught. They are only saying that we have to prove that there exists unique choice of P naught and Q naught so that distance of P naught, Q naught is less than or equal to distance of P comma Q for all P belongs to C1 and Q belongs to C2. So I think this way we are done with this question. Okay. So I hope you have liked all these solutions. Questions were little difficult, you can see, and they have given questions from all type of chapters. You can see here you can start with this question I can put into AP sequence and series. They have this question I can put into limits. This question is of complex number. Then this Newton-Leibniz use of differentiation. Then this is altogether different question. We cannot put this into any JEE syllabus, but yes, you can call this as a general question based on understanding of all the mathematics of JEE syllabus and ISI and CMI. Then this question was again limit question. So you can see there are two questions on based on limit this year. And this question based on polynomial, you can keep this question again in quadratic. And the last question is a question of AOD, you can say. Okay, so this completes all the solution part of this session. Dear all, let me tell you, if you are preparing for JEE Advanced or you plan to prepare next year or next to next year, Vedantu Eklavya is one very important thing for you to know. So please Google it to know what exactly it is. It is actually going to prepare you for JEE Advanced on online mode or online platform, I can say. I am sharing with you this link of topper notice board where all the batches going on here in Vedantu we will be putting information on them, and what new things coming up you will be coming to know through this notice board. So please follow it, or you can scan this QR code also to go to this notice board. This is the link and this is QR code for those students who will be appearing next year in JEE Advanced. You please join this Telegram channel. We will be putting all important information in this channel. Similarly, for 2024 aspirants, dear all, we are putting all the solutions of JEE Advanced, KVPY, and very soon ISI and CMI also on this YouTube channel, where you will find solutions of question wise and alternate solutions also you will find there. So please go through this, please visit this YouTube channel. Okay, so this is all for today. Thank you so much everybody. Take care. Bye.